Alright, so we did one of these yesterday, just looking at a graph and trying to pick apart different characteristics or properties of it. On page 151, we're going to try another one. So just like yesterday, I want you to try some on your own, just to see how you can do, become comfortable with some of these. I want you to do domain range zeros, greater than 0, less than 0. I think you guys can tackle the left and right end behavior. We're going to talk a little bit more about that today. Type of function, increasing, decreasing, max and mins. We'll do point of inflections and concavity together because that's a little new for us. But if you want to try it, I mean, I'm not going to stop you. Band people, how was your trip the last 2 days? Pretty good? Have fun? Good. Bless you. Bless you. All right, let's check out our first box. How about domain of all real numbers, range from -infinity to 6 with a bracket. X-intercepts, we have -5, -2, and +2 with multiplicities of 1, 2, and 1 respectively. How do we do? Do we want to go over any of those?
Does anybody have money for DECA?
That's cute, Autumn. It's cute. You too. Yes. All right. So this x-intercept of -5 and -2 and +2. So all these are x-intercepts, but notice how they're different types. So at this x-intercept, the graph goes straight through. Same thing's kind of going on at 2. But the x-intercept at -2, the graph just touches or bounces. So if a graph is going straight through an x-intercept, that's signifying a multiplicity of 1. Okay, the factor of x plus 5 and x minus 2 would evenly divide into this polynomial, whatever equation it is, just once. Whereas the factor of x plus 2 would evenly divide in twice. Is that okay, Rachel? Yeah. Okay, you're welcome. All right, next box, we're talking about above x-axis versus below x-axis if we're greater than 0 or less than 0 in terms of those y values. So above x-axis, we have -5 to -2, and then -2 to +2. Below x-axis, -infinity to -5, and 2 to infinity. How did we do? Pretty good? All right. Left end behavior. As you trace your graph on the left-hand side, notice how the graph goes down. So the y values are going towards -infinity. If you trace the right-hand side of the graph, it also goes down. So the y values, again, are going towards -infinity. The type of function, I'm popular this morning. Let's see, the type of function, we can say quartic, but I'm curious as to what you guys said as your reasoning. Anything for because? Thank you. Did we label it as quartic? All right, why did you do that? How did you know? Yeah.
It's multiplicities, add up to 4, the graph is recurrent.
Okay, so that you can look at two different things. If you look at those multiplicities we identified, 1 plus 2 plus 1 is 4. So we can say multiplicities add to 4. You could also look at the maxes or mins, okay, like those humps and bumps. We have 3 humps or bumps, which signifies a quartic function. It's one more than how many humps or bumps you have. So either one of those should be fine. How do we do on the end behavior and the type of function? Pretty good? All right. Increasing, if you trace the graph from left to right, where does your pencil go up? We'd have -infinity to -4, and then -2 to 1. For decreasing, your pencil would be going down from -4 to -2, and 1 to infinity. How do we do for those intervals? You guys are killing it this morning, okay? Relative maximums. So we're looking for high points. You could say -4, 3, Okay, there's a high point on the graph. You also have another high point at 1, 6. Okay, so you can label that one as well. Relative minimums. Okay, low points. We have one at -2, 0, happens to be an x-intercept. Okay. So those are the high points and low points on the graph. Are any of those absolute maximums or absolute minimums? Like the highest or the lowest? Yeah.
1, 6 is the absolute maximum.
There we go. Okay, that's the highest the graph goes. Do we have an absolute minimum? Why'd you guys say no? That's good, I saw the head nods. Why is there no lowest point? Yeah.
Because it goes down like
We have some arrows, yep, going down forever, so it's never ever going to reach a lowest point. Looks good. How do we do overall? Pretty good? Alright, so let's go ahead and tackle the points of inflection and concavity. This was kind of new to us yesterday. Points of inflection can happen at 3 places. Can we list any of those 3? Remember any of them? Yeah? Alright, an x-intercept with a multiplicity of 3. Did we label any of those in our characteristics? No, notice how we had multiplicities of 1, 2, and 1. Okay, so we have no x-intercepts with a multiplicity of 3, so we don't have to worry about that. What about one of the other 2 places? Yeah? In between a max or a min, did we label maxes and mins? Yeah, so we probably have some points of inflection to look for there. What about the third one? It's kind of the harder one of the 3. It relates the other 2 somehow. Yeah? It's a lot to say, isn't it, right? Yeah, it's in the middle of that x-intercept of multiplicity of 3 and a max or a min, whatever one it might be. But we don't have to really worry about 2 of those 3 options because we didn't even label any multiplicities of 3. So let's go ahead and try to look at the maxes and mins we identified. If we can find the middle of them, that would represent a point of inflection. So if these are the maxes and mins, and we were to like draw a little dot where we think the middle might be, those are the points of inflection that we're going to try to find. Okay, so it looks like we have 2 of them to look for in this case. So maybe we'll divide this into 2 spots. Let's take a look at the first one on the left. So the max and the min for that spot is the -4, 3 and the -2, 0. So the point of inflection is in between those. What's in between -4 and -2? Yeah. -3. And what's in between 3 and 0? Or 0 and 3, if you want to think about a number line. We got 1.5. Okay, so that is the coordinate of this point of inflection in the middle of that max and min. We'll eventually use that to help us with concave up versus concave down sections, but let's go ahead and try to figure out this other point of inflection. So this other one has a minimum of that 2, 0, or sorry, -2, 0, and a maximum of 1, 6. Let's go ahead and find the middle of those. Alright, in between -2 and 1. Exact middle. Yeah. -0.5, alright, and then in the middle of 0 and 6, looks like we'd have 3. Okay, so there's the coordinate for that point of inflection. So now that we know the coordinates, we're going to utilize those to help us with the concave up and concave down sections. So if you were to trace your graph from left to right, and then stop when you reach a point of inflection, how would you describe the curvature of that section you traced? Is it concave up like a regular parabola or concave down like an upside down? Yeah. Concave down. So the interval for that first section would be negative infinity to the x value of that point of inflection where you stopped. And notice how we already labeled that as -3. Okay. If you continue to trace your graph, stopping at the next point of inflection, how would you describe the curvature of that section? Regular parabola, upside down parabola. Yeah, regular parabola, so that's like a concave up. Okay, so that section goes from point of inflection to point of inflection. So we're going to go from the -3x value from the first point of inflection to the -1/2 x value from the second point of inflection. If you continue to trace your graph, we don't really encounter another point of inflection to stop at, so this is our last interval. Notice how that section looks like an upside down parabola, so that's another concave down interval. We're going from -1/2 to infinity. Good refresher from yesterday? Remember doing that? Perfect. How are we feeling with these characteristics? Notice how you were able to do like more than half of them on your own. Maybe the point of inflection stuff was a little fuzzy, okay, but hopefully we'll start to get the hang of that as well. We doing okay with those characteristics? Perfect? All right, let's go ahead and bust out our graphing calculators. We're going to take a look at this idea of left end behavior and right end behavior a little bit more today. We'll see how far we can get because the bell's going to ring fairly shortly, but we'll just wrap it up when we get back. So what we're going to do in this chart on page 157 is we're going to take a look at a bunch of different functions, a bunch of different polynomials, roller coaster graphs, and we're going to try to find a pattern between the way the equation looks and how the end behavior looks. Meaning on the left-hand side, do we go up and down, up or down? How does that relate to the function? On the right-hand side, if we go up or down, how does that relate to the function? We're going to try to find those connections. Okay? So what I want you to do on your graphing calculator, we're going to turn it on. Where do we go to graph something? Remember our buttons? Yeah. Y equals. Okay? If you have anything in there, go ahead and clear it out. And I want you to type in the first function. We'll have 2x squared minus 3x plus 3. Before we hit graph, let's go ahead and fix our window so that we're all on the same page. I want us all to use -5 to +5 in every direction, just so we're all seeing the same picture. I mean, not 5, -10 to +10, and you can count by ones. All right, once your window is set, go ahead and hit graph. So there's our polynomial shape, okay? Notice how the function we typed in is quadratic. It had a power of 2. So our graph should look like a parabola. Kind of makes sense. That's what's showing up. So based off of this graph and the equation, we're going to fill in some kind of key things to look for. So when you take a look at this equation, is the degree, meaning the highest exponent, even or odd? Yeah, even. We have a power of 2. Okay, it's quadratic. Is the leading coefficient, meaning the number attached to that x squared term, is it positive or negative? Yeah, positive. We have a positive 2 out front. Okay, so those are two things we can identify from the equation. Now, based off the graph, Does the graph rise, meaning go up, or fall, meaning go down on the left-hand side? If you were to trace that left end behavior. Do we notice how it's rising, going up? Okay. Does the graph rise or fall to the right, meaning that right end behavior, if you were to trace the right-hand side? Notice how that's rising as well. Okay, so we're going to take the time today and go through all of these different equations and use the calculator to at least help us figure out the rise or the fall portion. You should be able to just look at the equation for the first two columns. Okay, now to make this a little quicker, I'm not going to make all of you do all of these. Okay, can my first row up here do numbers 2 through 5? Okay, my front table, Grace and my ladies in the back, can you do 6 through 10? All right, and then my gentlemen, ladies, and 2 gentlemen over here, can you do the last 4? Okay, so you're not going to do all of them, just do your little sections, but then we'll eventually fill all this in so we have all the information. Alright, we'll wrap that up when we get back from break. You guys have a happy Turkey Day.